In this video, we're going to look at what a polar coordinate is and how it relates to the rectangular coordinate system we're accustomed to seeing. Now, our rectangular points are based on the horizontal and vertical displacements from the origin. And when you look at the graph paper, it makes a bunch of squares on it, and it allows us to count in terms of our displacement going from right to left, up and down to plot our point. We all know this. Now, a polar coordinate is not in terms of its horizontal and vertical displacement from the origin. It is based on the direct distance from the pole and an angle of rotations. All polar coordinates are written in terms of r by theta. Now, the pole, you can think of it as kind of the origin per se of the polar coordinate system. A polar graph looks a lot like a spider web almost, where it's the set of a bunch of concentric circles, where in the very center here we have our pole. And the polar axis is the right-hand side of the x-axis right here. And I have all these concentric circles of varying radius measures, where the first circle is a radius 1, the second circle has a radius of 2, and then 3, and so forth. Where whatever the r value is would tell me what circle I would be on. If r was 1, I'd be on the first circle. If it was 2, I'd be on the second. 3, I'd be on the third. 4, I'd be on the fourth. Now, the theta measure is the number of degrees or radians rotated off the polar axis, which is the right-hand side of the x-axis, in the counterclockwise direction if my angle measure is positive, just like what you do on the unit circle. So our polar coordinate that is written as r by theta, all right, we have our polar axis, which I said, think of it in terms of the right-hand side of the x. R is the directed distance from the pole to that point. And theta is the angle of rotation, the counterclockwise direction off the polar axis. Now, if I were to superimpose the polar point, or I guess the polar graph on top of the rectangular graph, we would form a right triangle. So I have my pole here, and then we have our polar axis, and then I'm going to put our point that lies somewhere right here. All right, so this point is x by y, and it's also we can get to it by doing r by theta. So they land in the same spot. Now, the distance from the pole to that point in terms of the polar coordinate system would be equivalent to r. Now, the rectangular coordinate system, if I bring a vertical line down and to the polar axis, I form this 90, and the rectangular coordinate system tells me that the horizontal part is equal to x and the vertical part is equal to y. So I have this right triangle here. Excuse me. Now, Pythagorean's theorem will allow us to relate the three sides of the triangle together, which allows me to say, all right, well, x squared plus y squared is equal to r squared. If I wanted to know what the r was for the polar point and I was given the Cartesian coordinate, or the rectangular point. Now, we also have theta that would go in here, so the angle of rotation off the polar axis. And I could even relate the x and the y to r and theta, where if I use some right triangle trick, where cosine of theta is equal to adjacent over hypotenuse, and sine of theta is equal to opposite over hypotenuse. And if I multiplied both of those right triangle trig expressions by r, moving r to the other side, we would get two more, I call them conversion formulas, where x equals r times cosine of theta, and y would equal r times sine of theta. And we would get to a point where we would use those conversion formulas in a future video. Now let's look at, well, how would we go about graphing a polar point? All right, and I have 4 different examples because our polar coordinates, we can be given a positive radius measure, a negative radius measure, just like we could for the theta values and the angles. And so this first point we have, it's a polar coordinate, so I have to keep in mind that the first number's r and the second number's theta. And so I want to plot the polar point 3 by pi over 4. Well, the fact that the radius is 3 means that I'm going to be somewhere on this circle here that has the radius of 3. So it's going to be somewhere on that circle there. And the angle measure, pi over 4, means that I need to rotate 2 pi over 4 on this circle. So pi over 4 is going to be right here. And so my polar point is going to be the intersection of that angle of rotation of pi over 4 to the edge of that circle that we have. And so there's my point, P. Okay? Now let's look if we have a positive radius and a negative angle measure. So I want to go and plot the point 2 by negative 255 degrees. Well, the 2 means that we're going to be on this circle that's on the radius 2 line. And I want to rotate to negative 255 degrees. Well, negative 255 degrees means that I'm rotating clockwise 255 degrees. Well, so 255 degrees negative, so there's 180. And then 255, that is 15 degrees shy of 270. It's going to put me right here. So that angle is negative 255 degrees of rotation. All right, now let's talk about, well, what if the radius is negative? How can you even have a negative radius measure when we know of a radius as the distance a point is from the center of a circle? Well, in terms of the polar coordinate system, we can't necessarily think of these as distance measures, but in terms of, well, what radial lines would I fall on? Well, the fact that r is 4 or negative 4 means that I'm going to be on the outer edge. So the circle that has the radius of 4, I'm going to fall somewhere on there. Now, the angle measure is pi over 3. So I would come up here to 4, where 4 pi over 3 is. All right, so this would be positive 4 pi over 3, this point. Since I have a negative radius measure, I would actually go on the opposite side of the circle. All right, so I would pass through the pole and go onto the opposite side of the circle, and that would be the location of this point P, where I have the negative 4 as the radius and pi over 3 as the angle measure. So the negative radius, what it does is it projects you through the pole, and it's on the other half of the circle. So it's actually pi radians away from where 4 by pi over 3 is. Okay, and then we got one more here. Let's look at when we have a negative radius, because we're another polar point, and a negative angle measure. So the way I would do this is I would go to my circle where I have the radius of 3, all right, which is going to be that one there that I indicated. And I'm going to go find the point positive 3 by negative 210 degrees. So I rotate negative 210 degrees. So negative 210 degrees is going to put me right here. So this point, actually, let me make it like a little X here. So that is the coordinate 3 comma negative 210. Now, that's not, we wanted to have a negative radius. So what we would actually do now is we would have to project back through the pole along that same line that that negative 210 degrees rotation's on. And that's going to put us right here at this point. So this is my point P. Okay, so we just saw how to graph the polar points, and it should have started, as you were going through that process, it should have made you start to wonder, well, isn't there an easier way that I could have written some of these coordinates so that way I wouldn't have had to deal with negative angle measures or a negative radius where I had to project back through the pole? And the answer is yes. In fact, there's an infinite number of ways that you can write these polar points because of our coterminal angles, where I could continue to do multiple rotations and land in the same point, or I could rotate in opposite directions, or by making that radius negative. There are a bunch of ways to write polar points. Now, in this exercise here, we're going to write 3 different ways to get to the same polar point that's given. And by the time we're done with this process, we should have a polar point with both positive radius and positive angle measure, or I could make one of those or both of those negative. So that way we have all cases accounted for, and we're staying under or less than 1 full rotation. And so here in this first problem, we're given the polar coordinate r by theta, and r is 3 and theta is negative 195 degrees. And I want to go to where that point is. Well, I would go on the circle radius line of 3 and rotate negative 195 degrees. So I'm rotating negative 195 degrees along that circle, and that's going to put me right here. All right, so this is the polar point that is provided. Now, one of the things that I would do is say, all right, well, what is another way to get to that same point with the positive radius? Because I should, by the time I'm done, I should have 2 points with a positive radius and 2 with a negative. Well, instead of rotating counter or clockwise, let's rotate counterclockwise, so that way I would have a positive angle measure. So if I rotate it around this direction here, what the number of degrees I actually be rotating would be 15 degrees less than 180, so 165 degrees. Now, notice what the relationship is between those two, because I don't actually have to do this graphically, is negative 195 degrees. Well, all I did is I made a coterminal angle to that. If I added 360 degrees to it, you would get 165 degrees. So there's a way to do this without looking at it on the graph. All right, so I now have 2 total points. I want a total of 4. So now let's make one where we have a negative radius and let's say a positive angle. So by me making the angle, or excuse me, the radius negative, what that means is I have to land on the other half of the circle. So I would have to land right here where I'm marking this X. And because it's a projection through the pole in the other half of the circle. So if I'm rotating around and I'm having a positive angle measure, I would rotate almost a full circle to get there, which would give me, it'd be 15 degrees shy of 360, so 345 degrees. Now, I want you to look at the relationship between the angle measure that we just had, the 165. So we had 165 degrees. If I wanted to get the angle measure to be on the other half of the circle, all we have to do is add half a revolution, 180 degrees, and that gives us 345 degrees. Now, lastly, we want a negative radius and a negative angle. Well, the negative angle means we're going to rotate clockwise to get there, which means that I would only rotate negative 15 degrees. And once I had that 345 degrees, all I had to do was take 345 and subtract a revolution from it, and that gives me 15 degrees. There's a way to do it by hand, and there's a way to do it by looking at it graphically. All right, now let's look at doing one of these problems where we're given a polar coordinate in radians to work with. So we have the coordinate -4 by 7 pi over 12. So -4 is the radius, 7 pi over 12 is the angle measure. Now, the fact that this radius is negative means that when I do my rotation of 7 pi over 12, I gotta remember to go on the other half of the circle. So I'll be on the radius 4 circle here, and let's rotate the 7 pi over 12. 7 pi over 12 is going to put me right here. All right, so I rotate the 7 pi over 12. And this coordinate that we have has to actually go through the pole onto the other side of the circle, and it puts me right here. This is where my polar point is. So we want to write 3 other ways to get to that point. Well, since we're already given a negative one, a negative radius, let's find the second way to get to that same point P with the negative radius. And this time let's go negative radius and negative angle of rotation. Well, X marks the spot on the wrong half of the circle that I want to rotate in. And so graphically, instead of rotating counterclockwise, we're going to rotate clockwise here and go all the way around to figure out the number of radians I'd have to go to get there. And the number of radians I would go to get to that same point would be -17 pi over 12. Now, another way to get that point without having to look at it visually and to graph it is that we had 7 pi over 12. All we did was we created a coterminal angle. So that means I need to add or subtract a revolution. Well, I need the negative angle measure. So I would subtract 2 pi from 7 pi over 12. And that gives me -17 pi over 12. Now, let's find another way to get to that point P. But let's use a positive radius measure. And so let's start with the easier one, positive radius, positive angle. So I would start on my polar axis, I'd rotate counterclockwise and figure out the number of radians I would go to get to that rotation where P lies. Well, it is going to be 1/12 past, well, pi over 12 past 3 pi over 2, which would make us have 4, 19 pi over 12. Now let's say I did not have the graph that I wanted, or the graph to look at. What I could do is, remember, when I have the negative radius, I am landing on the wrong half of the circle. So if I took this 7 pi over 12 and I added half a revolution to it, which halfway around the circle is pi. So if I take 17 pi over 12 and add a pi to it, that's going to give me 19 pi over 12. And the last one we have is if we had a positive radius and a negative angle measure. Well, we know where to land, so all we would do is we would rotate clockwise off the polar axis and figure out the number of radians I would go to get there. And the number of radians that you would rotate in the clockwise direction would be 5 pi over 12. So my angle is going to be -5 pi over 12 radians. Now by hand, once I had this 19 pi over 12, all I needed to do was make a coterminal angle. So take 19 pi over 12 and subtract a revolution from it, subtract 2 pi, and that gives me -5 pi over 12.